Introduce Luiz Cheim. He's a senior principal research and development engineer at Hitachi University and a member of the Forbes AI Advisory Board. A pioneering innovator with multiple patents, including the ABB Transformer Inspection Robot, he has led groundbreaking work applying AI and machine learning to power systems, diagnostics, and predictive analytics, and is a frequent keynote speaker at international engineering conferences. Let us welcome our speaker.
Thank you. Can you hear me well? Yeah? Okay, so I promise to do my best not to bore you to death. Although I must confess it's a hard task. A little bit of 1 minute here of history. I'm an electrical engineer by education. Yeah, so and after maybe 30 years of experience, I decided to go back to school to learn new things. I thought was, and maybe that is one of the alternatives that we should be looking at, particularly those that are concerned with jobs, losing jobs in the times of AI. There are lots of concerns regarding that. I think that those that will be out of jobs is those that do not use AI. And if you want job security, start learning this very fast in several ways. For example, in my view, everything that is repetitive, that is, it doesn't require a lot of brain to be done, will easily be replaced by machine and machine learning and so forth. So, and that's good news because everybody will free up time to do something more enlightening and learn new skills and so forth. So, yeah, so in Hitachi, I'm involved now with service and AI. Let's say, the front end with customers and applications of AI and so forth as an organization. But what I'm going to show here briefly, because again, I don't want to tire you unless you are desperate to learn about these things, details about what I'm going to show here. I will not show details, just en passant, in passing. What we've done. But this, everything with the exception of the last slide, is not directly related to generative AI. Okay, so I separated some applications that I was heavily involved, proposed, and so forth. And as you can see here, I will not read them all here, but all of them use machine learning fundamentally, and again, not Gen AI, with the exception of the last one that I called Superminds, and I will explain why in a minute. Okay? So the first application was one that when I went back to school and I did some interesting courses with, for example, I started learning online, and then I learned about some courses at Stanford University for statistical learning. I started doing those courses, MIT, Harvard, and I got actually some certificate in the process, which helped me, let's say, to move into this new, let's say, field that was, let's say, strongly showing to be important in what I was doing, because I was heavily involved with, forgot to mention that, in writing algorithms that would help us understand the condition of an important asset in the electricity industry that's called transformers. So not transformers in machine learning, but transformers as an asset, big transformers, power transformers, where you have substations near your house, or sometimes you see the little ones hanging on pole-mounted transformers. So how can we assess the condition of those guys once you gather data from their operations? And I was writing algorithms about that for an application that the company we were developing as a company. And then I detect that I had some limitations. I had important limitations. By the way, I had the opportunity to discuss here with some very smart colleagues about statistics. And some of my limitations were in statistics. And that's why I mentioned statistical learning was my first step into, let's say, refreshing my knowledge about math, statistics, and then helping me with machine learning in the future. Okay? And that was very important. One of the applications is this one here, that from the date, SIGRE, if you are not familiar with, SIGRE is an international organization. It's like a club in the electricity industry that embraces people from the many areas of electricity and utilization, production, transmission, generation, and so forth, like the IEEE, similar to the IEEE here in the US, North America. But SIGRE is headquartered in Paris, and it's very important globally. So you have people in Asia, South America, Africa, people joining this organization from all over the world. Okay? And our company has a strong presence at SIGRE. And anyway, I was lucky to be awarded this Best Paper Award in 2018. Now, let's think about that together. Okay? Look at the title, Machine Learning Tools in Support of Transformer Diagnostics. If I got this award in 2018, this work was done in 2016-17. Because I had to first do the work, and I'll in a minute tell you what the work was. And second, I had to apply for this. I had to present the paper. I had to send the paper, the abstract, the paper. All this process took 2 years. So this is an old stuff, right? 2016, 17, this is very old. Already, 2018. And what was the work about? Well, since I learned those, let's say, new skills from the courses I mentioned to you, I said, well, let's test this thing here. Let me separate 1,000 transformers for which I have data, operational data. 1,000 transformers, not many. For us, it's a lot for the type of work that was done here. And let's gather data, all types of data, let's say operational data. I will not bore you with the details again, unless you are desperate, which kind of data. But just think about that. If you have a car, what would be operational data from a car? Well, the oil level of the engine, the tires, the condition of the tires, the age of the car, and so forth. Operational data. I gathered the same from our famous power transformers, 1,000 transformers. And then those 1,000 cases had been assessed by the professor there, which was a team of experts from the company that had already assessed the condition of those 1,000 transformers. And here was the question that I posed to myself. Can this algorithm learn to assess the condition of those transformers as well as the experts did in analyzing them? That was the question, okay? Which had an excellent result, okay? I will, again, not bore you with the data, 24 features for those that are more familiar with machine learning. So 24 features, 1,000 transformers. The black marks indicate missing data. So I had to handle things like missing data, outliers, and as you guys know, all these fun things that we learn to do when we learn these techniques, right? I had to handle all that, and in the paper, I described in detail what I did. I think I forgot to mention that I got this award because it was the first paper in our industry that did that kind of thing. Again, 2018, guys. That was the presentation of the paper, okay? And then, as you can see here, these box plots show the multiple algorithms that were trained with the data that I had. And I select the best one here, the one that you see on the top right, the box plot, that shows the variability or the variance of the accuracy of the learning curve or the learning process of the algorithm. That algorithm was the one that I selected and said, okay, you are the champion. Now let's use your capability and let's submit 200 new cases here. 200 new cases that had never been seen by the algorithm. And tell me what you think about those 200 cases. And from the confusion matrix, I guess you guys are more familiar than I am with this. The confusion matrix on the bottom right tells you the impressive capacity of that machine learning algorithm to classify those 200 transformers as well as the experts would do or had done with those new cases that the algorithm had never seen before. Okay, so this was the, let's say, the essence of the work. A very impressive result for an algorithm that learned from data, learned from the assessment, supervised learning, how the experts would assess the condition of those transformers, and then provide an assessment of new cases with such an impressive accuracy of 97% approximately. Okay? So, first application. Second one is, I will go briefly, is a technique used in our industry to classify dissolved gas analysis in transformers, transformer insulating liquid, oil, mineral oil most of the time. And that pentagon is called the Duval pentagon. Not going into the details unless you are desperate again. But as you can see, it's a very complex geometry. That geometry utilizes 5 gases, as you see here at the bottom right. Okay, you have 5, let's say, axes of this pentagon. Each axis represents a gas, a dissolved gas, a combustible gas, acetylene, methane, ethane, and so forth. Like when you take blood sample from your own body, and the doctor analyzes, oh, maybe the oxygen here level is too low, and so forth. So those parameters are statistically significant, or may not be. In the pentagon, you want to analyze where those gases, when combined in the pentagon, where they fall in those regions. And each region may represent a problem. But the pentagon itself is very complicated as a geometry to classify individual samples of dissolved gas analysis. So what I did here, the work that was done, was, well, maybe if we generate artificial data to cover the whole pentagon, as you see at the top right, and use those cases to train, again, machine learning algorithms, maybe we have a very simple way, like a function, a simple output. You know, if I have these components, these 5 gases, what is the diagnostics? Well, here's the diagnostic. Impressive output, impressive accuracy as well. This was around, I think, 2019, I think, this work. Forecasting, I mentioned here in the morning that to the panel here, that's something that I missed. For us, forecasting can be extremely important and useful as well. For example, load. The curves that you see here represent the load of a transformer. The load means the power that is going through the transformer. If we can predict that load with at least 1 hour in advance, maybe we can take actions to avoid failure, to avoid, let's say, overheating of the transformer. We may shed load between different transformers, knowing what is coming next. So load forecasting is extremely important to us. I trained machine learning algorithms to do this, and the results were impressive. By the way, as you can see, again, here the box plot showing the different algorithms and their variance in terms of the prediction capability during training. And the ones that had the best results, surprisingly to me, were linear regression models, okay, for this, for load forecasting. But I also use neural nets and so forth here, okay. So as you can see here, the dots, you know, the orange dots, if I'm not mistaken, I'm not wearing my glasses here. Yeah, the predicted are the orange ones, the green ones, and the green curve is the actual curve for testing. Again, never seen by the algorithm during training, and as you can see, the results are impressive in terms of prediction capability, forecasting capability, okay? We need some improvements still when you talk about 2, 3, 4 hours ahead, still working on that. Same technique was used for detection of failure mechanisms in one component of transformer that's called bushings, as you see on the top right there. If you take a picture when you go through near a substation, near a house or a factory or something, you'll see the transformers have those funny spikes that are called bushings. Those bushings have the intent of connecting the windings inside the transformer to the power system, to the power network. Without those bushings, you couldn't have transformers as small as the ones you see. Although sometimes they may, weigh like 250 tons, they may have 50,000 gallons of mineral oil inside and so forth. They may be very big. But without those bushings, we would be in trouble. So bushings are essential. However, they fail as well. It's a very important component that may fail. And we measure some operational parameters of them from time to time. Users, like Duke Energy and so forth, they from time to time, they stop the transformer, they stop the substation, let's do some measurements. And in those measurements, they detect things that may or may not be related to evolving faults. Okay? And with this algorithm here, similar to the forecasting algorithm, we were able to detect with excellent accuracy the development of faults in those components. And we could then raise the flag and say, this transformer is going to be in trouble very soon. Okay? Now, one of my favorites is a probabilistic fault tree that is our proposal as well. When you look at this tree, although I'm not showing the details of the tree here, each branch represents a component, a major component of the transformer. Okay? Transformer you see at the bottom there. For example, the branch at the left may be related to the cooling system. You see fans there. The second branch may be related to, let's say, the conservator, as you see at the top. The next branch may be related to the bushings, and so on and so forth. Like in a car, you may have a branch that is related to the tires, another to the engine, the comfort, the age, and so forth, the use of the car. So this tree was built based on what we call failure modes. Okay? If the tire doesn't behave very well, how or through which process can the tire lead to the car failure? Fundamentally is what this tree does. But I added a probabilistic. What is the probability that since you have a problem with your tire, that this will lead to a car failure? So we added a probabilistic, let's say, layer on top of this failure mode. And this failure mode is still under development, okay? True, it will be, Aldo, a true application in asset health, okay? So where the user of transformers will have this as a, if you like, a digital image of the operational parameters of the transformer. And then some of these nodes may be fed by online sensors, which may change the probabilities dynamically. That is what I represent there with that variable distribution. Okay? Some other nodes may be fed by laboratory data from time to time. You take your car to the service, you have some new data there, and you bring that data to your database. So it's every 6 months, 1 year. So laboratory data, maintenance data, and so on and so forth. And this tree, this probabilistic tree, will then use users or customers' statistics. Okay? With those statistics, then we can propagate these probabilities. And in the end, provide the user with indications of, let's say, the criticality of their individual transformer, all using the so-called Bayesian networks. You guys there must be experts on that. Okay? Now, the one that I told you was my last slide, and I want to summarize this again to give you guys some time to relax, is the Superminds Project. It's the only one that is related to generative AI. Okay? But I must confess that it is related by chance. Because this is a proposition of ours from 2019, which got a patent granted in March 2022. What happened in 2022? Who remembers? In November 2022. Something came to play. Very important. ChatGPT. Yeah. So a few months later, ChatGPT came to our, let's say, world, right? But why I say this is highly related and by chance? Because in those days, by the way, I did a course with a professor, Professor Malone from MIT, and he wrote this book, Supermind. And as a tribute to him, I called this project Supermind as well, and you will see why. So here's the idea. The idea that I proposed was, let's take all of our knowledge about transformer, and let's put it in a database, a knowledge base, here on the bottom left. And let's have an engine, okay, at the top that will learn from that database. You may relate that to ChatGPT already, right? And then, but when I wrote the patent, you know what it says? Natural language processing. Using natural language processing because there was no ChatGPT, there was no generative AI. By the way, I never learned in the schools I went to, I never learned about how to create the generative AI thing. That's why I say it's an interesting coincidence. Now, I propose that through natural language processing, the AI tool would learn from this database. And to do what? Well, we needed more things. Okay? Would learn also from a database, an anonymized database of transformers that we do not hold, that we do not operate. Why? Because these transformers are in the hands of users. Which users? Duke Energy, Con Ed, okay? Florida Power, utilities that have those that operate, we sell them. We sell those transformers, but we do not operate them. So we do not have that data. So the proposal here was, well, let's have them on board together with us, and let's have an anonymized database so that we all can benefit from this engine. But why, you may ask yourself, why would they join this? Why would the utilities, like Duke, for example, join a private company to do this? Well, because the proposal continues. First of all, it would be anonymized, so nobody is seeing what is going on in terms of data. They have to believe us. So this could be audited, and then to demonstrate to them that it is anonymized. But then we can query this. We can query the knowledge base and the data. And then the engine can tell us what is going on. You know, all the correlations, all the statistics related to those similar transformers. For example, you drive a Mercedes 2023 S. Well, the engine then could tell us, or could tell you, what is going on with everybody else that have Mercedes S 2023 or similar design. What is going on? Where do you sit statistically? More could tell you where are the issues with your, not only your Mercedes, but you may have a fleet of Mercedes, right? A fleet of transformers. So where are the pain points? And what should you do to avoid failure, to minimize, let's say, risk of failure and optimize maintenance costs, for example? Okay? And then make recommendations. You should do A, B, or C, or all of the above. So if you think about this, this is very similar to what agentic AI does, okay? But that's not how we proposed. We didn't know this name, we didn't use that name, but we got a patent for this, Supermind, okay? That is fundamentally the project that is more related. And by the way, we are working on this. And of course, how can we benefit from this, we as a company? Well, if we have all this engine working, we can learn better. We can learn from the engine itself, from the data, from the recommendations, and we can improve our own procedures. Okay, because, I mean, like, I like to use the example of cars. We can have better cars in the future. We can optimize the cars. We can minimize the problems that our users are having with the asset. Okay? So we can learn better ourselves. So that's fundamentally the idea. Some applications, I hope I didn't bore you to death, because, you know, it's such a space. Well, you know, our keynote speaker here was talking about so broad things related to including God. And I'm here talking about transformers, which is such a boring and specific subject, right? So nothing close. But gives you an idea of some applications in the industry that we've been seeking and trying our best to use these things with. And there is more to come. Okay? We are still, let's say, is our first steps, I would say, into this new world. And we hope for the best for the industry as a whole. Okay? Thank you.
Thank you very much. We're going to open it up for a round of questions, if anybody has any questions. Yeah. And we have a microphone coming up. Thank you very much.
Hello. Thank you very much. Great presentation.
Thank you.
So the first few projects that you did with machine learning, a couple questions. How did you handle the samples or the process variables that you use for your transformer, for instance? Because I'm assuming a lot of that data, like the oil and the other things that you saw there, like room temperature, you didn't have online instruments for that. So you have to do all that through lab testing. And without being able to timestamp this when it happened or when the failure happened, by using these samples that were all combined on every 6 months or every year, able to do a regression model to be able to forecast and use those, you know, the points that fit the curve. How are we able to do that without all the online instrumentation that it takes to accomplish that?
Yeah, thank you. Excellent question. Thank you very much. That study, that was my first exercise with machine learning, as I said, 2016-17, was fundamentally applied to offline data. So although we are very much concerned and looking for solutions for online data, as I mentioned towards the end, but that first application was totally offline. Now, if you think about it, online data is the exception rather than, let's say, the rule. Okay? Our industry is extremely conservative. If you select, for example, Duke Energy. If you ask Duke, anybody at Duke, so how many of your transformers, let's say large transformers, have online sensors on them? I bet that would never be higher than 10%, something like that. Maybe they selected 4 or 5 very important transformers and said, oh, these guys here, we need, because these monitors tend to be expensive. And companies, is understandable, companies would never, let's say, the intent is if they decided strategically that they would monitor with sensors their fleet of transformers, that should be applicable to the whole fleet. But then, if you think, for example, one single sensor for dissolved gas analysis may cost 40, 50K US dollars. So if you have like AEP, American Electric Power, headquartered in Ohio, but they are present in 13, 14 states in the US as a transmission company. I think it's the largest transmission company in the US. They have only working with one of our applications, one software, 7,000 transformers. So if you think about that, one sensor, if you want to apply that to 7,000 transformers, you multiply 7,000 times 50K, and you see the cost of adding one online sensor. And then, but you may need other sensors, like I talk about dissolved gas, you may have moisture sensors, you may have partial discharge and other sensors that are very sophisticated as well. So still today, online monitoring is the exception rather than the rule, okay? And that application was to offline. That's the first part. Second part is, which is related to your question, is history. Because, okay, I take one sample every year for multiple parameters. I have that. But should I analyze, historically how this thing, how this unit behave? Yes, in principle, yes. But the effort I did was I analyzed the last sample, like the last picture that was taken of the operating condition of the asset. Okay, like you have your car, so it was the last measurements of the tire, thickness of the thread, the oil level, and so forth. I took the last picture. I didn't take the history, which would be, let's say, a better assessment. How experts analyze the data, they look at the history, okay? But I simplified my life at that stage and used only the last record.
One more question. When you train the model again with new data, because you get new samples or new lab data.
You don't train again?
You don't train again?
No.
So you don't change the algorithm after?
No.
You do it once or once?
That is the meaning of training. So, for example, I forgot to mention that I had 1,000 transformers, okay? I separated 800 transformers. Actually, the algorithms did that for me. Separated randomly, because I didn't want the bias of selecting the transformers that I thought would be more adequate for training. So the algorithm selected 80%, okay, 800 transformers for training. And then once they were trained, they said, okay, now you have these 200 here that you have not seen during the training phase. So I used the same algorithm that was trained before. Don't retrain. Now, is it possible to retrain? Yes. It's called dynamic training or retraining. For example, if you think that your data may be changing statistically, you may retrain your algorithm. But what you are doing is you are fine-tuning your algorithm, okay? You are not... the correct way is you train with part of the data, typically 70 to 80%, and then you test or validate it with 20 to 30% of the data that the algorithm has never seen before. Does it answer your question?
Definitely, thank you.
I think there was a question here before going to Anderson.
Thank you very much, Luis. A couple of questions. The first one is, do your service engineer experts feel threatened by this application? Because essentially the application may be replicating their knowledge, and maybe they feel impaired because of their job. And the other question is, what do you see for the future from this point on, given what is happening?
Yeah, thank you, Aldo. Good questions. Well, yes, some may feel threatened. Some experts may feel threatened. I actually had a hard time when I decided to do this first attempt with the data, 2016, 17. Some experts, some diehard were concerned. but they retired. So when you say how they feel, fortunately or unfortunately, we are losing this kind of knowledge. We are losing this kind of workforce. And is a very important knowledge. And I would say maybe I wouldn't call it a secondary benefit. It's a very important benefit of using these tools is to keep the knowledge and the state of the art of the knowledge from disappearing. Because as you guys know, particularly in engineering, and my company, for example, we exist since maybe 100 years. And can you imagine the engineers 100 years ago thinking, oh, let's create an infrastructure of the data that guys in 100 years' time will be using it for AI. So nobody ever thought of anything even close. So, and that is one problem for us, industrial, let's say, outfits, that heavily machine-based and so forth, that we are not AI and data prepared, you see? So this is happening as we speak. We are changing, okay? Because of several needs. One of them is we are losing expertise as well. And these engines, they can help us to keep that knowledge as well. Second point, you had a second...
Yeah, how do you see
the future, yeah.
For the future,
Yeah,
from the point where you are?
The title I chose for this last slide, the Superminds and the actual application, the patent and so forth, is related to exactly that. The way I see it is I find it fundamental, the cooperation human-machine. Okay, I don't think we should ever leave 100% to the algorithms and to machines, as it is very hard to leave it to humans only. I think the cooperation should always be there. And the critical thinking behind the use of these tools must be always there. We must be critical of the outputs. We must be critical of recommendations from these systems. We must be critical of the outputs. Okay, so we must have people prepared to analyze and make the best use of these tools.
Hey Luiz, great presentation. So nice to hear your applications of machine learning to power systems problems. One of the things that caught my attention was the load forecasting. We're also working a load short-term load forecasting more to the grid level, and it seems you are working more in the distributed load forecasting for transformers. So my first question is this for substation level transformers or distribution transformers? And then the follow-up is, are you also planning to include distributed load forecasting in the Superminds? Thank you.
Yeah, thank you. Yes, this application is related to the online monitoring, because the assumption is, and we have solutions for that, like we have a box that you can connect to individual transformers. And one of the things that that box will do is to monitor continuously the load and ambient temperature and a few other parameters. So since we have that, we can learn from that as well. So even if you don't have history, you can build history or historical data. Since you have that application, you have the machine, you have the box there collecting load information. Like your car 20 years ago, let's say, okay, you could measure oil level, but now if you take your new car to the company that supplies it, the service, okay, they will say, oh, but you see, over the last 5 years, this is what happened to the oil level of your engine, so it's not a new problem. So they can trace it, because now you have means of monitoring and storing that data somewhere. So the same is happening with transformers. We're installing, let's say, facilities now that can build history. Since we have that, assuming that we have that, we can continuously then treat that data, learn from the data, and try our best to estimate what is going to happen as well on an individual basis. But this would be more applicable, now back to specifically your question, to transmission in, let's say, larger transformers, because the cost of such, not only the algorithm, but having the, let's say, the facilities there, monitoring continuously the parameters is high. And that would not be justifiable to small transformers. I would say medium to large transformers at substation level, but on an individual basis, yes. Okay, thank you.
One more question over here.
And there's
Microphone 7.
I'm surprised you guys are still alive.
Must be the coffee.
Yeah, I wanted to ask, is it possible, since the things like, for instance, you were talking about gas monitoring in the transformer oil is so expensive, is it possible to use learning algorithms to learn things that are inexpensive to observe, that correlate to the things that are very expensive to observe, so that you can learn how to observe this stuff very inexpensively over a larger quantity of transformers? Things like bushings and other things, just by observing behavior of the transformer.
Yeah, thank you for the question. Yes, so we we always have this internal fight, because think of, again, let's go back to cars. Think of, let's say, Toyota car, okay? So what do they manufacture? It's a car. So their concern is the engine, is the quality of the car, is the whole thing. They don't manufacture tires. They don't manufacture, if you have sensors like the cameras today, the modern, they buy it somewhere, and they force their suppliers to do a nice job of keeping those costs low, or to have a competitive, let's say, car out there, because the market is so competitive. The same with us. We are not manufacturers of sensors as such, but internally we have lots of proposals. Why don't we develop this sensor based, for example, on fiber optics, that does this and does that? And then when it comes to our management, R&D, global, and so forth, well, we manufacture transformers, we don't manufacture sensors. By the way, we make billions in revenue selling transformers. How much you expect from this cheap sensors there? So we have always this, let's say, difficulty in having or not having these cheap sensors available in the market, although we have proposals for that as well. But you are right. The ideal situation would be if we could have a Christmas tree of sensors that would monitor individual transformers. That would be very cheap, but that's not available, unfortunately. So almost every sensor out there is in the thousands of dollars range per unit. Now, again, if you think about a fleet of transformers, because your concern as an asset manager is not to solve the problem of one transformer. You have 7,000, so, right? So I'm not sure if I address your...
Well, I think what I was wanting to ask is, are there other things that you can observe?
Oh, yeah.
That correlate to something that the expensive
And we do.
tell you? And can machine learning help you figure out what those things are, so that you can observe those instead, and use those to predict, if we put in this sensor, this is what we would probably see.
And that first exercise was exactly that. Those parameters that you saw there, they are measured anyway. For example, the bushing, it's called the capacitance of the bushing and power factor, 2 parameters, right? So the utility will measure that every 3 to 5 years. They will stop everything, let's measure that. And that is what I was using there. So I'm not asking the user to add cost to have those parameters, because those parameters are available not frequently, not continuously, but it's the best we can do. The PGGA, dissolved gas analysis, they send, unless something is happening, they know something is happening to the transformer, all things, let's say, stable, they will take an oil sample once a year. And that oil sample per transformer will cost $100. So instead of having one online sensor there that costs 40K, they pay $100, $150 to send that sample to a laboratory, typically is an outside laboratory, And like we do with our blood test, go to a laboratory, right? It's not your doctor that does that, sends it away. It's the same, they send it away. 2 weeks later, if they are lucky, they get the answer back. And that is the kind of data that I was analyzing with that application. It's offline data, data that is typically available to the user, that would not require, let's say, continuous, which is different from the last application that I mentioned with the probabilistic tree. That one, we are preparing to receive online data as well when the data is available. Okay? So I think there was another one there. There.
Oh.
Yeah.
One more question over here.
Oh, I'm surprised. I thought you guys would die of boredom.
Thank you for your sharing. My question is not technical one, but a more industrial question. And I'm a PhD student, and it's my second year. So with AI and machine learning,
I'm sorry to hear it.
with AI and machine learning everywhere, so how can non-CS background student can stay there competitive? Like we can use AI tool, but we cannot do really well like CS student. So do you have any recommendation that which field should we prepare to try to beat them?
Thank you very much. I was just joking, saying I'm sorry. I'm a PhD myself, so I went through the process as well. So, excellent question. And my answer to this, and I don't want to be repetitive, particularly to my team here, where we discussed how can we improve graduate programs and all that. So my feeling as an old engineer, I've been around to more than 40 countries around the world, talking to users, talking to colleagues from my own company, is that we are very weak as engineers, we are very weak in statistics. Okay? So I think if you want to differentiate yourself, have a strong statistical background. Know what you are doing. Know how to assess the algorithms that ChatGPT is just spitting there and telling you that that's a good code. The simple area under the curve where you do assessment of the accuracy of an algorithm. Why area under the curve? You know what area under the curve does? You are comparing the rate of false positives to false negatives. So why? False positives and false negatives. If you understand that the probability, I was talking to, I'm not sure if he is here. Nicholas, are you here? No. Sometimes I surprise myself that my colleagues don't know what actually probability means or statistics. For example, you have a normal curve, okay? And the mean value of that normal curve is 100. And then I ask them, what is the probability? Whatever 100 is, let's say summer temperature, the average summer temperature in Raleigh, 100 Fahrenheit. Okay? Let's assume it is true. Now, but this is a continuous distribution. I ask them, what is the probability if you close your eyes and you select one variable, one value of temperature from this distribution? What is the probability of getting 100? They open their eyes like that when I say zero. Probability is zero. The probability of having the mean value is zero. Nobody believes me. Why? Because engineers, I'm sorry to say, are very weak regarding statistics. And I'm an engineer myself. I said I had to go back to school and so forth. So people don't realize that the probability, when you talk about continuous distribution, is area under the curve. There isn't such a thing as the probability of one number. The probability of any number is zero. But you see, you may be surprised. Some of you may be surprised as well. So we shouldn't be surprised, because this is so basic. And the engineers, in general, lack that knowledge. And by the way, If it were not for statistics, bye-bye ChatGPT, bye-bye machine learning. The foundation of all this starts from one thing called linear regression. Why? Because in linear regression, the essence of linear regression is minimizing the sum of the squared residuals. When you minimize the sum of square residual, you find your ideal line fit in linear regression. Guess what? You know where that equation is? In neural networks. When you do the back propagation, it's the same equation. You are minimizing the square of the error. But you see, statistics is the foundation of machine learning and AI. So, if I had to suggest something to you and to your colleagues, be strong in statistics. You make a difference. You see, some of you may look at me and say, this guy is smart. I'm not. This is basic stuff that everybody should know. But we don't. Why? Why we don't? So, in the US, my kids grew up here. In the US, I would say, if I had to name the biggest fault is in high school in the US. The weakest link here in the US, in my opinion, middle school is okay. High school, I'm sorry. And it comes from there. Then kids come to college. My youngest son graduated here at NC State. So kids come to school, engineering school, well, statistics, maybe, I don't know, 3 months or something like that. Most of it formulas. And so, not good, guys. My feeling is not good. Okay? I don't know if that answers your question.
I think we have one final question over there.
Yeah.
I was interested in, you were mentioning high school. I think one big problem is that we aren't actually preparing people for the stuff that they're actually going to see in college now. We still have a high school curriculum that's essentially like built on kind of early 20th century needs, but we aren't actually teaching, and very often when we try to modernize it, we're just going too fast. We're not actually teaching people logic, for example, which is what all computers run on. We're not teaching people how to actually do stuff with statistics, or teaching them elementary combinatorics, like very simple things that they're actually going to use, for example, if they ever do statistics or computer science.
Yeah, I thank you for your comments. I may be the last person. I'm not in education, so you guys are experts, And I was highly disappointed at myself during the presentation here, the panel, that a lady that was sitting there asked if the panel saw any deficiency in our system that could be improved from graduates and so forth. And people said that they are fine, that they don't, and I stayed quiet. When I tried to say something, Aldo cut me off because the time was over. But I don't know, guys. When my oldest son graduated from high school, we still lived in St. Louis, Missouri in those days. I had been transferred around. And when he graduated from high school, I remember the principal asking the question, who here is going to go to, how you call those schools for professional schools or something like that. So maybe 15 kids raised their hand. Who is going to the military? Maybe another 20 kids raised their hand. Who is going to college? So you could count, like maybe 1, 2. So something is not right somewhere. I went to Harvard. I have a project with Harvard. I'm not saying Harvard just to sound posh or something. We have a project, a development under the DOE, Harvard and Sandia National Lab. I went to Harvard and I didn't see any American kid there at the graduate level. something is wrong somewhere. You have to tell me. I'm a foreigner here, just a visitor. You know, and you guys are discussing here curriculum and so forth. So I'm about to retire in a few years. I'll be out of the market, not causing trouble like today here. But yeah, it's time for us to, as a country, maybe to rethink these things, you know. Maybe that's the reason why we have one person making $1 trillion a year and the rest of the population making how much? Right? Anyway, food for thought. Yeah.